In a high concurrency database, thousands of transactions operate simultaneously, accessing shared data without colliding. Think of each as a sailboat. Upon entry, it is assigned a unique, immutable marker, like the red stripe on this sail. This timestamp determines its priority and path. This differs from traditional locking, where a transaction stops and waits for others to finish. Here, the right-of-way is predetermined by the time of entry. If two transactions attempt to access the same data item at once, the one with the earlier timestamp, the older boat, is given priority. Because priority is fixed at the start, the system resolves conflicts by either allowing a boat to proceed or sending it back to the beginning to restart. This prevents the circular dependencies, where two boats sit idle, waiting for the other to move. This approach shifts concurrency control from reactive resource grabbing to a system of preset chronological navigation. For this navigation to work, the data item queue must keep a record of every transaction that interacts with it. Every data item maintains an R timestamp. This is a digital log of the most recent transaction to read this specific coordinate. It also tracks a W timestamp, recording the timestamp of the last transaction to modify its value. As a boat navigates, the system constantly compares the transaction's timestamp against these two stored values. These tags allow the concurrency control manager to determine if a transaction is attempting to access data in a way that violates the chronological order. Consider the system in a high-speed environment, where multiple transactions are attempting to read the same data at once. When transaction TI requests a read, the system checks if its timestamp is smaller than the data's W timestamp. If it is, TI is attempting to read a value that has already been overwritten by a transaction assigned a later point in time. Because TI cannot see a value that effectively no longer exists in its timeline, the transaction is aborted and restarted with a new, later timestamp. If TI is newer than the W timestamp, the read succeeds. The R timestamp is then updated to whichever is larger, its current value or TI's timestamp. This ensures that no transaction can witness a state of the database that was created after that transaction was supposed to have finished. Write operations are more restrictive. They require a dual check against both the recorded read and write timestamps to ensure the timeline remains consistent. If TI attempts to write, but its timestamp is smaller than the data's R timestamp, the system rejects the request. This is because a younger transaction has already read the existing value and proceeded under the assumption that the value was current. Allowing TI to write now would invalidate that younger transaction's work. Next, the system checks the W timestamp. If TI is older than the last writer, it is trying to produce an obsolete value. In a strict system, this obsolete write triggers a rollback. This preserves conflict serializability, ensuring the final schedule is equivalent to a serial order based on these timestamps. The write rule prevents older transactions from reaching forward and altering data that younger transactions have already moved past. Every rollback consumes CPU cycles and forces the transaction to repeat its work. In cases where a write is merely obsolete, there is an opportunity for optimization. Suppose TI tries to write an obsolete value, but no younger transaction has actually read the data yet. Thomas's write rule provides a solution for this specific case. The system can simply ignore the write instead of rolling back the transaction. Since no transaction from TI's future has seen the data, TI's write is harmlessly skipped. The boat continues its course. This moves the system from conflict serializability to view serializability. The schedule remains correct because the resulting database state is identical to a serial execution. By discarding these unnecessary operations, the protocol increases the number of transactions that can commit without a restart. The evolution of this protocol involves eliminating the need to overwrite data at all. Instead, the system preserves every version of a data item ever written. In this architecture, Q becomes a history of versions. Each one is tagged with the timestamp of the transaction that created it. Under this model, a read request never fails and never waits. It simply identifies the version in the stack that matches its own timestamp. Multi-versioning is a refinement of the timestamp principle that prioritizes high availability and storage capacity over transaction restarts. By making time of entry the primary mechanism for ordering, timestamping protocols provide a mathematical path to serializability. The core trade-off is clear. The system avoids the wait times associated with locks, but it accepts the cost of restarting transactions when the chronological order is violated. While basic timestamping is a theoretical model, its logic, specifically in the form of multi-versioning, is a core component in the design of modern, high-performance database engines.